Hey, you, ever get that itch to really, understand how things work? Not just on the surface, but deep down?
Uh-huh.
Like what makes fire fire?
Mm-hmm.
Or how do we even figure out what tiny bits of matter are made of?
Right. That kind of curiosity.
Exactly. And that's the sort of rabbit hole we love to dive into here. We take some core info, unpack it, so you get those satisfying aha moments.
Yeah, without you having to spend, like, hours digging through stuff yourself.
Precisely. And today, we've got a really fantastic collection lined up, 11 different science experiments.
It covers quite a range, actually. Chemical stuff, physical phenomena. Think of it like a high-speed tour, maybe.
A high-speed tour, I like that. Through some really fundamental science principles, all based on practical, hands-on things.
And our goal is basically to pull out the key science concepts and maybe some of those surprising little details that make you think.
Okay, so we're working from a document that outlines these experiments, right? The steps, what you'd expect to see.
Yep. Forget the dry textbooks for a minute. This is about seeing science in action.
Love it. Okay, let's kick things off. First up, making oxygen.
Right. Experiment 1. The preparation and properties of oxygen. So this one shows how you can get oxygen gas just by heating a specific chemical.
Which one is it?
Potassium manganate is this purple stuff. You heat it and out comes oxygen.
And how do you know it's oxygen?
Well, the key observation, the classic test, is you take a glowing, splint-like wood that's smoldering, and you put it in the gas.
Boof.
It relights, bursts back into flame. That's oxygen's signature move, basically. It loves to help things burn.
Gotcha. The document also mentions colors when washing up.
Yeah, that's interesting, too. It hints that the original purple stuff, the potassium manganate, has actually changed into something else.
So the heat breaks it down, thermal decomposition.
Exactly. You see the gas, and you see evidence the starting material changed. It's neat.
It really is. So thinking about that, what other, maybe more common things, release oxygen, even if it's a different process? Something for listeners to ponder.
Good question. Okay, moving on from gases. Experiment 2 takes us into the world of polymers.
Plastics. They're everywhere.
Absolutely. And this one is kind of like a sorting game, as you said earlier.
Right, how does it work?
You take different plastic samples, PET, like water bottles, PVC, HDPE, like milk jugs, LDPE, PPPS, all those common types.
Mm-hmm.
And you see if they float or sink in 6 different liquids. Each liquid has a very specific known density.
So some will float in one liquid but sink in another.
Precisely. And that pattern of floating and sinking across all the different density liquids, it acts like a unique fingerprint for each plastic.
A fingerprint. That's a great way to put it.
Yeah. The notes show, for example, PET is pretty dense, sinks in everything, but PP, polypropylene, is much less dense. It only sinks in the least dense liquid.
So it's all about density mass for a given volume, a fundamental property.
Mm-hmm. And you can use it to identify materials? Makes you think, doesn't it? Look around you at the plastic stuff.
Yeah.
Any guesses which might be denser than others?
Definitely makes you look twice at your recycling bin.
Yeah.
Okay, next up, something very relatable. Food energy. Experiment 3.
Right. This one uses a simple form of calorimetry, basically measuring heat.
How do they do that?
They take a small weighed bit of food, like a nut or a piece of cheese puff, maybe,
Okay.
and they burn it underneath a container holding a known amount of water.
So the burning food heats the water.
Exactly. You measure the water temperature before and after. That temperature change lets you estimate how much energy was released from the food when it burned.
So you're capturing the heat energy. The notes mention comparing this to food labels, like for cheese.
Yeah, they use cheese as an example. The packaging might say something like 1,638 kilojoules per 100 grams. You can compare your experimental result scaled up to that.
But it probably won't be perfectly accurate, this setup.
Oh, definitely not perfect. It's a simple version. Lots of heat can escape to the air, not all go into the water.
Right.
And maybe the food doesn't burn completely, or the heat transfer isn't 100% efficient, but
it shows the principle.
Exactly. It shows that food stores chemical energy, and burning it releases that energy as heat. Just like our bodies metabolize food to release energy.
Gives you a real sense of what those calories or kilojoules on the label actually mean. How might thinking about that energy content affect food choices, I wonder?
Something to chew on. Okay, let's switch gears. Experiment 4. Making something totally new from basic elements. Iron and sulfur.
So starting with just iron filings and sulfur powder.
Yep. And first, it's just a mixture. You can still pull the iron out with a magnet, right? The sulfur's still yellow and powdery.
Okay, just mixed together.
But then you heat it.
And this is where the magic happens.
Well, the chemistry happens. The key observation is the mixture starts to glow on its own, even if you take the heat away for a moment.
Whoa. A sign of a reaction.
A definite sign a chemical reaction is occurring. And the crucial thing is, after it cools down, the stuff you're left with, it's different.
How different?
Try the magnet again. It won't pick it up. The iron isn't iron anymore. It's chemically bonded with the sulfur to make iron sulfide, a new compound.
Wow. So new substance, new properties.
Yeah.
Completely different from just mixing them.
That's the core idea of a chemical reaction versus a physical mixture. It's a fundamental change. Can you think of other elements that combine to make something totally unlike the starting materials?
Maybe like hydrogen and oxygen making water. Very different stuff.
Perfect example. Okay, experiment 5 brings in another force. Electricity, chemistry and electricity.
This sounds cool, like writing with chemistry.
Sort of. You dissolve salt, sodium chloride, and water. Then add an indicator, maybe methyl orange, which changes color depending on acidity.
Okay.
Then you soak filter paper in the solution, and you take a simple battery, connect it to 2 carbon rods, like pencil leads.
Electrodes.
Right, electrodes.
Yeah.
And you use one of the electrodes connected to the battery to sort of draw or write on the damp filter paper.
And something happened.
Yes. Color changes appear where the electrode touches the paper. The notes say methyl orange turns yellow at the positive electrode.
Why? What's that like?
It's electrolysis. The electric current is forcing a chemical reaction. At the positive electrode, conditions become acidic, making the indicator change color. If you use universal indicator, you'd see different colors at each electrode, showing different ions being produced.
So the electricity is causing chemical changes you can see with the color.
Exactly. You're visualizing the products of electrolysis. It makes you think, where else does electricity drive chemical changes in daily life? Batteries charging, maybe? Metal plating?
Yeah, lots of places once you start looking. Okay, next, something familiar. Burning things. Combustion, experiment 6.
Right. Specifically looking at what a candle produces when it burns. We know it gives off heat and light, but what else?
Invisible stuff.
Invisible stuff. So they burn a candle inside a sealed gas jar for a bit, then they test the air inside.
How?
2 simple tests. They use blue cobalt chloride paper. If water vapor is present, it turns pink. And they use lime water calcium hydroxide solution. If carbon dioxide is present, the lime water turns cloudy or milky.
And what do they observe?
Just what you'd expect for burning candle wax, which is a hydrocarbon. The cobalt chloride paper turns pink.
Showing water.
And the lime water turns cloudy.
Showing carbon dioxide.
Yep. Simple tests, but they confirm the basic products of burning hydrocarbons, CO2 and water. What other fuels do you think produce the same things? Petrol, natural gas.
Probably. Most of them are right. If they're made of hydrogen and carbon.
Yeah.
Okay, experiment 7 sounds a bit more mathy. Determination of relative atomic mass.
It is a bit more quantitative, yeah. Using magnesium.
So how does this one work? Measuring atoms seems tricky.
Well, you don't measure atoms directly, but you use a reaction. You take a very precise known mass of magnesium ribbon.
Okay, weigh it carefully.
Exactly. Then you react it completely with excess hydrochloric acid. This reaction produces hydrogen gas.
Ah, and you measure the gas.
Yes. You collect all the hydrogen gas produced, maybe in an upside-down burette or measuring cylinder filled with water, so you can measure its volume accurately.
Got it. Mass of magnesium in, volume of hydrogen out.
Right. Now, here's the clever bit, stoichiometry. The chemical equation tells you the ratio of magnesium atoms reacting to hydrogen molecules produced.
Like 1 magnesium atom makes 1 hydrogen molecule or something like that.
Exactly that ratio for this reaction, yes. And we know that a certain number of particles, a mole of any gas, occupies roughly the same volume under the same conditions.
Okay. The molar volume.
Right. So from the volume of hydrogen, you can calculate how many moles of hydrogen you made. And because of the 1.1 ratio in the reaction, that tells you how many moles of magnesium must have reacted.
Ah. And since you know the mass of that number of moles of magnesium.
You can calculate the mass of 1 mole of magnesium, which is its relative atomic mass.
Wow. That's clever. Using a simple reaction in gas volume to find a fundamental property of an element. So why is it important for scientists to know these relative atomic masses accurately?
Oh, it's fundamental for everything in chemistry. Understanding formulas, balancing equations, predicting reaction yields. Everything builds on knowing how heavy atoms are relative to each other.
Foundational stuff.
Yeah.
Okay, experiment 8 takes us to group 7 of the periodic table, the halogens.
That's right. This one looks at the reaction between iodine, which is one halogen, and zinc metal.
What do they do?
They mix solid iodine. It's kind of a dark purplish black solid with zinc powder and a bit of alcohol just to help them mix.
And what happens?
They observe a few things. One is often a temperature change showing energy is released. Another key thing is the purple color of the iodine disappears.
Meaning the iodine is being used up.
Yeah.
Reacting.
Exactly. And after the reaction, if you let the alcohol evaporate away, you're left with a new solid substance.
Which is?
Zinc iodide. It's a salt. So you've directly synthesized a salt from its elements. Zinc metal and iodine, the halogen.
Cool. Direct combination. So what other elements might react directly like that to form salts? You mentioned halogens.
Well, yeah, other halogens like chlorine or bromine react readily with many metals. Think about sodium reacting with chlorine to make sodium chloride. Table salt. Lots of possibility.
Right. Okay. Experiment 9 builds on this. Reactions of halogens.
It does. This one is more about comparing the reactivity within the halogen group.
Oh.
They set up a grid, basically. They take solutions of the halogens, chlorine water, bromine water, iodine water, and mix them with solutions containing halide ions, potassium chloride, potassium bromide, potassium iodide.
So testing every combination.
Every combination. And they look for signs of a reaction, usually a color change. For example, chlorine is more reactive than bromine. So if you add chlorine water to potassium bromide solution...
The chlorine kicks the bromine out.
Exactly. It displaces the bromide ions, forming bromine, which has a distinct orange-brown color in water. But if you try adding iodine water to potassium bromide, nothing happens.
Because iodine is less reactive than bromine.
Precisely. So by doing all the combinations, you see this pattern emerge, this reactivity series. Chlorine is more reactive than bromine, which is more reactive than iodine.
Like a clear hierarchy. The experiment also mentions universal indicator paper.
Yeah, just to check if the halogen solutions themselves are acidic or anything, which can sometimes be relevant.
Okay, so based on that pattern, that reactivity trend, what would you predict if you took fluorine, which is above chlorine in the group, and reacted it with potassium chloride?
Well, following the trend, fluorine is the most reactive halogen of all, so you'd definitely expect it to displace chlorine from potassium chloride. Very vigorously, probably.
Makes sense. Okay, one last experiment, number 10. This one sounds intriguing. The sublimation of air freshener.
Ah, sublimation. This is about a change of physical state.
Not melting.
No, sublimation is when a solid turns directly into a gas, skipping the liquid phase altogether.
Like dry ice.
Exactly like dry ice, which is solid carbon dioxide sublimating. This experiment uses a solid block air freshener.
What's the setup?
You put the air freshener block in a beaker, maybe sitting over some warm water just to gently encourage the process. Then you put another beaker, maybe with ice in it, on top.
So warm below, cold above.
Right. And the observation is the solid air freshener block slowly shrinks, disappears over time.
Without melting into a puddle.
Correct. It's turning directly into a gas. And sometimes you might even see tiny crystals of the air freshener reforming on the cold underside of the top beaker.
Oh, like the gas hits the cold surface and turns back into a solid deposition.
Precisely. So you see the solid vanish and then reappear somewhere else. It's quite neat. Mothballs do this too.
Huh. Are there practical uses for sublimation, besides air fresheners and mothballs?
Oh, yeah. Freeze drying is a big one. Removing water from frozen food as ice vapor preserves it really well. It's also used in purifying some chemicals.
Fascinating. Wow, that was quite a sprint through 11 experiments.
It really covers a lot of ground, doesn't it? From making gases, identifying plastics, measuring energy, forming compounds.
Electrochemistry, combustion, finding atomic mass, halogen reactivity, and even physical state changes, like sublimation.
It just shows how even fairly simple-looking experiments can tap into really fundamental, important scientific ideas.
Definitely. It's a great reminder that science isn't just abstract theory. It's rooted in observation and, well, doing stuff.
Yeah.
Hopefully this encourages people to see the science happening all around them.
Absolutely. Keep that curiosity going.
So here's a final thought to leave you with. Reflecting on all these different experiments, these different concepts, which one surprised you the most? Or which one felt most connected to your own life? And maybe more importantly, what new questions did this little tour spark for you? What else do you certainly want to know? Because really, that's where the real understanding starts, right? Asking the next question.